In this presentation, we will understand what is D flip-flop and how we can make a D flip-flop by using a SR flip-flop. You already know what is SR flip-flop, and I have made the truth table for SR flip-flop because this is the important thing from which we will derive the conclusion for our D flip-flop. Let's examine this truth table. You can see if I want to store 0, then I have to give 0 1, and if I want to store 1, then I have to give 1 0 as the input. My S will be 0, my R will be 1, then I have 0 stored in my SR flip-flop. If my S is 1, R is 0, then I have 1 stored in my SR flip-flop. Now you can see a very interesting thing, that this S and R are always complement to each other. When S is 0, R is 1, and when S is 1, R is 0. So why we have to give this S and R individually? We can just give one input to this flip-flop and complement the other. That's what we have to do to get the D flip-flop. Now you might be thinking that what about this case? You can see this is an invalid case. We are not going to use it. So if you just want your data to be stored, then you can have your D flip-flop, where D is what? Data. And it is one of the most commonly used flip-flop because you just give your input, store the data, and remove the clock. Your data will be there. So it is a very important flip-flop, and JK flip-flop is the another most widely used flip-flops that we will see. So what we have to do to convert this SR flip-flop to D flip-flop is to, let me extend this input. I will take this input, use a inverter, and give the output of the inverter to R, and this input I will call as D. So now you can see that when D is 0, it means when S is 0, I will have R as 1. That was this case. When D is 1, it means S is 1, and my R is 0, it means this case. So I need only a single input, that is my D, and to get the other I will complement it. This is what we do to have our D flip-flop by using the SR flip-flop. So I can make a D flip-flop like this. In my D flip-flop, there is a single input that I will call D, and I'm having my clock, of course, and the two outputs Q and complement. And this thing is what? It is actually, let me change the color for this. If I hide this circuit and take my clock out, so you can say that this circuit is inside this box. Now this is how we will make a D flip-flop. It's time to move to the truth table for D flip-flop. Okay, a very simple truth table. You will have your clock and a single input D, okay, and output Qn plus 1. Now when clock is 0, it means this circuit won't take any input, and the output will be what? The previous input. So Qn is my output in this case. When clock is high and D is low, it means what? S is 0 and R is 1. And for this particular case, I'm having Qn plus 1 as 0. So this is 0. Now when clock is high and D is 1, I will have my S as 1 and R equal to 0. It means this case, and I'm having Qn plus 1 as 1. And the other cases like S equal to 1, R equal to 1 is not possible in this D flip-flop because you can see a inverter attached here, and simply we cannot have this configuration. So this is the truth table for your D flip-flop, a very simple truth table. In the next presentation, what we will have is the characteristic table and the excitation table for the D flip-flop using this truth table. So see you in the next presentation.